Hello, and welcome to this presentation delivered by TMAC on data to decisions. TMAC works with businesses to accelerate their profitable growth and competitiveness by developing and improving their products, processes, technologies, and people. The TMAC mission is to increase the global competitiveness of the Texas economy by growing the extended manufacturing enterprise. So TMAC is part of the MEP National Network. Specifically, TMAC is the Texas representative of the MEP National Network. The MEP National Network is a unique public-private partnership that delivers comprehensive, proven solutions to U.S. manufacturers, fueling growth and advancing U.S. manufacturing. Since Texas is such a large state, TMAC has multiple representatives scattered throughout the state. They're comprised of 8 regional offices, all housed within institutions of higher learning, with an experienced staff of manufacturing advisors covering the entire state of Texas. Since 1995, TMAC has helped more than 6,200 organizations secure recorded improvements in revenue, cost optimization, and job growth. And these numbers are actually reported via surveys that our clients complete at the completion of our projects with them. So, who is presenting? My name is Cyrus Rahimzadeh. I've been with TMAC about 5 years. I'm a mechanical engineer and systems engineer by training, and I've been doing engineering work in the product development space for about 20 years now.
My name is Juan Paramo. I've been with TMAC for 16 years. My background is computer engineering, so I have done a little bit of everything, going from the microcontrollers, PLC, robotics, vision systems, and the latest, we're getting into is robotic process automation.
Excellent. So what's the purpose of today's presentation? The purpose of the presentation is to share the lessons learned by the TMAC technology team, which is myself and Juan. And what we're going to do is share our general approach and show some case studies related to how data can be used to make decisions. So what do we mean? We know that companies are required to constantly make decisions, and these decisions can be around the domains of profits, products, processes, technology, and people. Now, how do companies typically make these decisions? Well, they can be tempted to make these decisions based on expert judgment. Maybe they've been in the business for a while and they just have a gut feel. There can be hearsay. Maybe they go to a trade show and someone says, this is the latest whiz-bang solution that should be used. There's a lot of sales literature out there, which can be good or maybe not so good. Sometimes it's just out of exasperation. They just want some sort of a solution. And then many times we find that clients are hoping for the best.
And Cyrus, just to add to this, some companies make decisions based on partial information. And also, for example, like shadow spreadsheets. So, we have seen that as well. So, keep that in mind.
That's a good point. So what decisions have we helped answer? So this will be pointing to the case studies that we'll walk through. We've worked with a wire cutting machine manufacturer that uses the machine to produce different wires, lengths. We've worked on extruder heater performance, drying room performance, refrigeration system utilization, dye tank utilization, and water discharge. So we've worked in multiple domains looking at different types of equipment and different types of processes. So the first case study we'd like to walk through is a wire cutting machine performance. So on the left, you can see the current state that this owner had. Basically, there's a wire cutting machine where uncut wire enters from the left, goes through the wire machine that cuts it to some certain length, and can do a post-processing operation on the on the end of it to remove the insulator from the conductor, and the cut wire comes out the right side. And the question that the owner has was, should they invest in a new piece of equipment? Well, the real question we thought was, what is the utilization of this current piece of equipment? So what we did is developed a monitoring architecture. This particular system we developed around a VERMA system, utilizing an operator-actuated downtime and setup button. So this was a manual button that the operator would press depending on the scenario. We used a distance-based laser sensor to detect there was a part inside this machine that rotated with the frequency of each part being produced. So we could use that to count parts. And then we also had a current switch, which we used to calculate when the system was on or not on in order to determine availability. So on the right, you see this monitoring architecture, which shows the systems we used for the input, a representation of what the VERMA system looked like. It had a wireless gateway component to it. And on the right, we show what the visualization looked like. In this case, it was a visualization created in Power BI.
And sorry, just to add to that, basically the integration allow us to tap into the VERMA local database, and the Power BI web service had to use an on-premise gateway. So those are some technical details to keep in mind.
So what was the utilization of the current equipment? After monitoring the system for several weeks, we found that the data shows the OEE was about 19%. So the owner can use this information to focus on changing their workflow of operations to improve the availability and performance. So in this situation, maybe the best answer wasn't, let's get another wire cutting machine. The better answer would be, let's look at the process and get more utilization out of our existing assets.
And sorry, just to another quick detail is that Power BI just allows you a limited number of data refreshes. So and it also depends on the licensing that you have. So Pro versus Premium. So you can determine, or you can specify different times of during the day to make the data refresh.
Good. So the next case study revolves around an extruder heater performance question. On the left, you can see the situation. There was an extruder. It was one extruder of many in this customer's facility. We deployed a system. It's circled there in the red dash. So you have this orange box. That's the data acquisition system that we use to capture the power. So you can see over here on the right, we had a current transducer that went to the lines going to the heaters inside this extruder. And all that was to answer this question of, should the owner invest in insulating jackets for this extrusion equipment? So a question was, well, how often are the heaters on in the extruder, and how much power is really being consumed? So after monitoring the system for several weeks, the actual answer was, well, the data shows the heaters are rarely on. So in this case, there wasn't a business case to purchase the insulating jackets. Now we showed two graphs here, and they're time series data that came out of a Power BI visualization. On the left, we have multiple days of data, and it looks like the duty cycle is quite high. You see it looks very constant here at 10 kilowatts. But the reality is this data is so compressed on this time scale that when you look on the right and you now take this time scale for a 3-hour slice, you can see that many, many times the system isn't on at all. So what turned out was that the shearing forces inside the extruder to extrude the material out was generating so much friction that the heaters themselves weren't really on.
And sorry, just a quick technical detail. So in this case, we connected to a cloud-hosted database. So we didn't need the on-premise gateway, like the case before. And at the same time, like you mentioned on the graph shown on the right, we use the time zoom feature from Power BI. Very useful.
Yeah, Power BI has a lot of interesting features for different use cases. So this next case revolves around drying room performance. So in this situation, the owner has many rooms that are heated, and inside these heated rooms, they have their product, which has to cure or dry for some amount of time. And so the question was, should they adjust their drying process? The question that we tried to answer was, how long should the product stay in the drying rooms? So prior to us running this test, the process was, let's leave the product in for 24 hours, let's say, which is more tribal knowledge than an actual calculated time. So what we did was deploy some sensors. You can see on the left, it's a wireless sensors that communicate over Bluetooth to a wireless gateway. This is the gateway, and you have the little sensors. And we recorded the temperature and humidity of their product and gave them access to this time series data. So now that they have this information that we've provided, they can use this information with their quality control and process engineering groups to shorten their process time. So now that they have this data, they can use it as a tool to say, well, maybe rather than 24 hours, we could go 18 hours or 20 hours and get more product through their process and use their power more efficiently.
And Cyrus, just a quick comment on this. This was an off-the-shelf system.
Yes.
I know you're gonna present this in a future slide, but this was enough, and very robust and reliable. So if an off-the-shelf system is enough, that will be the first choice, rather
Yes.
than a custom system.
So the next system to talk about, or the next case study to talk about, was a company in Texas that makes a lot of cakes. And these cakes come off a conveying system and they're hot. And they immediately go through a refrigeration system to bring them down to a cooled state before they go off for packaging. So on the left side, you can see the hot cakes enter the conveyor, enter the room on this lower end of the conveyor. They go through a spiral conveyor that goes from bottom to top. And then once the cakes are cooled, they're then coming out of this refrigeration system and go on to the packaging line. So the owner wants to know if they should adjust their production process. So the question we tried to answer was, is the refrigeration system on when it should be? You can imagine that this refrigeration system takes time to get to the correct temperature. And likewise, especially in the Texas heat, it consumes a lot of power to get down to the operating temperature. So to better answer this question, we came up with a system where several things were measured. On the left, you can see a laser-based distance sensor that we deployed on the conveyor. This is the inlet conveyor to the refrigeration system. The cakes break this beam, and the system knows that cakes are entering the refrigeration system, so we can detect cakes entering. On the outside of the unit, we had this orange box again. It's pretty popular in these slides, that has a current sensor so that we can detect, is the refrigeration system on or not on? And on this next slide, we also had thermocouples inside the refrigeration system where we could detect, is the refrigeration system at the temperature that it should be or not? So this lets us know, is product in the system, the refrigeration system, is the refrigeration system on or not on, and is the refrigeration system at the right temperature that it should be?
And sorry,
Oh,
just to add to that, basically for the digital input, we got clever. Actually, you found out the hardware component to make this happen. So it's a timer relay. So basically, if we see a cake, the signal stays on until we see the next cake. So that allowed us in the database to keep track of the total time that the cakes are entering the system.
Yeah, that's true. So you can imagine these cakes as they're coming into the system. So going back to this image here, as the cakes are making and breaking this beam, that's an intermittent input. But the frequency of the data acquisition system reporting to the cloud service isn't necessarily in that same frequency. So what we did is between this sensor and this inside this box was a timer relay. So we were able to, when a cake passed it, keep that signal high for 5 minutes in this case, so that we were assured that we were reporting to the cloud service um, accurately.
Correct. And I believe, this was the first test as well of the Swift system that you will explain.
Yes, yes. So, what were we able to answer the question? Well, is the refrigeration system on when it should be? We identified opportunities to streamline the production to utilize the refrigeration system capacity. So what does that mean? Basically, this is a Power BI visualization of the data. And if you look in the bottom right, you'll see a bar chart. The lighter blue color is when the system was available, meaning the refrigeration system was on and at the correct temperature, whereas the shorter dark blue line is the indication that cakes were actually passing through the refrigeration system. So when we look at the disparity between the height of the light blue and the dark blue, this is availability that the client is paying for but isn't using because the system is at the correct temperature, it's on, but no cakes are entering the process. So the takeaway from this is that the client can use this information to either use the refrigeration system less or change their process upstream so that they have more consistent flow through the refrigeration system. This next case study is a dye tank utilization case. So there's a manufacturer we're working with that has a finishing company for different metal parts. And one of the operations involves a black dye tank that you see here in the image. And the question was, there's a product out there called UFOs, which are a type of floating insulator that floats on top of the surface, with the idea being that it insulates the system and then saves on power consumption, water, chemicals, etc. So the question that the client had was, is there a business case to use these insulators? Do they work or not for his situation? So what we did is we set up a data acquisition system where we monitored power going to the heaters in the black dye tank. And we also had a thermocouple inside the tank monitoring the temperature. Now we ran a test for a week with before the UFO insulators were installed to get a baseline. Then we installed the UFOs in the black dye tank. You can see them floating on the surface here on the image on the right. And then we reran the test for a week to see was there really any difference. So the question was, or the answer was, with the UFO insulators installed, the availability of the tank increased from 24% to 55%. And what does that mean? Basically, with the insulators floating on the surface, capturing that heat, the time to get up to temperature to where the black dye tank process was effective decreased, and the time that the system stayed at that operating temperature was increased. So he had more availability of the tank, but he could run product through it. And then he can take this information and say, okay, I'm going to get this much more, this increase in availability. He can make the business decision of should he deploy the UFOs on this tank or others, and when that makes sense for him or not.
And sorry, just to point out, for example, on the graph on the left, there's two axes. So Power BI allows you to graph a primary axis and a secondary axis to visualize, what's happening on the machine in this case, on the tank in this case. Additionally, it allows you to graph in different colors so you can visualize it.
Mhm.
So keep that in mind.
Yeah, and that really becomes handy with these time series plots, being able to have temperature and power on two different scales on the y-axis, but to overlay them on the time series graph. That does
Yeah,
help.
yeah, to understand, what's happening. Additionally, we also, did some edge computing. So basically, based on the temperature range, we're able to do some computing at the edge, meaning at the gateway, and be able to trigger some lights. You can see that we have the green, the yellow, and the red.
Yeah, and that's a good point to remember. That really helped their process because part of their internal process was to have one of his associates walk around and periodically manually verify the temperature. So having a system like this that one was monitoring the system for our purposes, but also we could affect that light at the edge depending on the temperature, helped his associates verify the system was at the right temperature.
Yeah, and just to give you some examples of edge computing, you can also basically average data before you send it to the cloud. You can take the max or the min, so you can do some processing, useful processing, before sending the data to the cloud.
That's a good point. So in this case study, we monitored the water discharge. So in the image below, you can see we're at a brewery here in Texas, and they have many processes that consume water. And as part of that process, they heat the water. So they're spending money to heat the water, use the water, and then it gets discharged. And their question was, should they invest in a system to capture heat from this discharge water? So the question that we tried to answer was, is there a business case to install this system to capture this heat? So what we did is we deployed a data acquisition system in their facility, and then we used a flow meter, you can see here, and this flow meter was in line to their discharge. So their process would run for, we left the system there for a week. It would run for several days. We're monitoring how much water is being discharged, and then we could capture that information to then to provide data for the owner to make an evidence-based decision. So what did we find? We found that we knew how much water was being discharged for the time that we were there, and then we could develop an annual forecast. So in this particular situation, we could say, well, this is how much water you consumed for a week. If this doesn't change, you're going to consume this amount of water in a year. We knew that the incoming temperature and the discharge, we knew what the incoming and discharge temperatures were. We knew the amount of natural gas it takes to heat that amount of water to whatever the discharge temperature was. And we could take all that information and turn it into dollars so that the owner could make a decision.
And sorry, just to point out, in this case, we use Google Looker visualization.
Correct.
So it's an alternative to Power BI. There are different alternatives such as Grafana, Tableau, and one that just came out to my radar is Azure Synapse. And that's basically to analyze huge databases, data lakes, data warehouses. So it's more efficient, for big data.
Mm. So those are the case studies. So now there's this topic of which data tool makes sense. And so we've got a little images here of, are you just working in your backyard and need a wheelbarrow? Are you trying to move a pickup load's worth of material? Or do you need an earth mover, right? And this really is a function of the use case, the cost, the complexity, and the maintenance required to affect the change.
And Cyrus, I will add the compatibility in the sense, many companies they have their infrastructure with Microsoft or they have with AWS or Google's, BigQuery. So yeah, that's another key point to consider.
So what is our approach? We've basically broken it up into 3 types. Again, based on the use case, cost, complexity, and maintenance. Now, on the leftmost image, there's a system that we've used called sensor push. This is what you saw in the drawing operation case study. This is a very relatively easy system to use and deploy. However, it doesn't have a lot of flexibility, and it's limited to temperature, pressure, meaning barometric pressure, and humidity. In the middle of the road, so this is more of the pickup situation, there's a sensor system that we started using called Swift sensors that we've integrated into some cases. And one of the benefits of this is that it makes very attractive dashboards that can be visualized on a cell phone or a PC. And it's a more open system where we can have anything with a 4 to 20 milliamp output, or let's say a 0 to 30 volts DC output. We can handle those inputs into the Swift sensor system and visualize them or track them as needed. And in addition, there are some off-the-shelf sensors that the company offers for monitoring things like temperatures and pressures. And those are the little white boxes that you see. And their sensors communicate over Bluetooth. So for example, you can see this is a current monitoring system down here, which communicates over Bluetooth from this sensor to this gateway. And we've just packaged it with some relays and power supplies to make it easier for us to deploy. And then at the higher level complexity, we have a current system. This is the famous orange box that you saw in some of these case studies. It's composed primarily of components from a company called Moxa, which has a Moxa gateway, and then it has an I/O card and a thermocouple card, and then some corresponding terminal blocks and relays that we use to handle our I/O. It also has a small system from a company called Fidget that we use as a backup system, and it can communicate over Wi-Fi using a hotspot. Because many times we find that clients have challenges and maybe they don't have Wi-Fi in the location where we need to monitor, or maybe their processes don't allow our system or any system to communicate with their network or their guest network. So at times we try to provide our own hotspot. And then the new plan system to come out, now it's this yellow box here, is very similar where it has many capabilities, but rather than using a Moxa-based system, it's using a product from Opto22 called Epic, which has this screen here. And it's very similar in that it has expansion cards for monitoring and controlling digital and analog inputs and outputs, as well as some power monitoring capabilities for those clients that are interested in monitoring electrical power consumption.
Yeah, Cyrus, I can tell you from Opto, I mean, they have opened the IoT universe, so they made their systems very flexible. So you can use Node-RED, you can use Azure, MQTT clients, for example, for HiveMQ, and Open UA servers. So it's very flexible.
Yeah, and the data component is very, it's something to keep front of mind when you're going down this path. So for example, with sensor push, there's no subscription, at least at the time of when we purchased it. There's no subscription to handle the data. You just use the sensor push app to access the data, and it's time series. With Swift sensors, there is a subscription to process the data or store the data in the cloud, and it's relatively moderate cost. Now, when you get into these customized systems, you have to be aware of what kind of resource you're going to use, whether it be Azure or AWS or something else. And then the costs are associated with the different tiers that you choose and the frequency of the data that's being transmitted. So there's different tools and techniques to handle the type of data traffic and the cost associated with that traffic as needed.
And sorry, just last comment, independently of the need, our philosophy is to have a standalone system ancillary, don't affect the process or the machine. So independently of the need, we always stick to that philosophy.
That's right. That's right. So that concludes this presentation. Again, you get to see our smiling faces. I'm Cyrus. My colleague Juan was on the presentation with me. Our contact information is below. It's smartmanufacturing@tmac.org. You can always go to the TMAC website. TMAC offers, in addition to data, dealing with data, TMAC also has many other services revolving around quality management, Lean Six Sigma, and other benefits that small to medium businesses may require. Our team's phone number is below. It's 817-272-5917. And to make it really easy, if you shoot that QR code on the right side, it'll take you to a contact form that you can fill out your contact information, and it'll go directly to myself and Juan.